Let's talk about the wave equation. What you just heard, of course, was a little bit piano music, and the music arises because hammers hit the strings of the piano, and then they make these beautiful sounds. And so what I'm plotting here in this graph is just one of these strings. From A to B, it is fixed in A and B, and then the string has a length L, and of course, to make this sound beautiful, it is under a lot of tension. Of course, another good example, which is even more standard maybe, would be the guitar. Alright, so here you see my strings. If I pull it, it vibrates, makes a beautiful sound. If I make it shorter, it vibrates and makes a different sound. This sound was not very beautiful. So the key to all this is the tension. This here plots the string as it is vibrating. And of course I completely exaggerated the picture. It would never oscillate like huge amounts. It's only very small amounts. But still, this is part of the string as it vibrates around. And so then T is the tension along the string. And of course, the tension needs to be high to make a good sound. So the tension will be important for everything we do. Another thing important is the angle. So you have a tangent line along the curve, and this makes an angle with the horizontal, and this is what I call theta. And then you can apply Newton's law for the string, and then Newton's law is a formula here on top. So rho is the mass density along the string. Delta x is the displacement from x to x plus delta x, right down here. And u will be the extension of the string away from its resting position. So then this says the second time derivative, or actually d by dt of rho delta x du by dt, is the tension at x plus delta x, so the upper point here, times sine of the angle, minus the tension at the lower end, sine of the angle at the lower end. This means the force will be made by the tensions and the angles relative to each other. Now this term minus alpha du by dt delta x, du by dt is a velocity, right? If u is a displacement, then the time derivative is a velocity, and this represents the resisting force. So the string wants to come back to the resting position. This minus beta u dx, this is the restoring force. The string doesn't like to be bent, it wants to come back. And then q, this term here, represents external forces such as gravity. Now if I look at the string, which is very light on a guitar, then gravity will probably not be very important. So later, in fact, we will throw almost everything out. We will argue that q is 0, that alpha is 0, that beta is 0, and the important terms will come from the tension. But for now, we keep them all in there. And now we divide by delta x. Okay, so then this delta x goes away, this goes away, this goes away. And here in the top, you might already see something which looks like a derivative showing up. And this delta x would go away as well. Let me show you what happens on the next page. Okay, so here we have the same equation. We have a time derivative of rho du by dt. And then this became an x derivative of the tension times the sine. The alpha term with the friction term, the beta with the restoring force, and the gravity term q. And now we make a whole bunch of simplifying assumptions. Important is that we have small displacements. For small displacement, we can approximate the sine by the tan. Okay, tan is also sine of theta divided by cosine of theta. Now, if the angle is small, right, then the cosine is close to 1. Cosine at 0 is 1, so if theta is very small, then the cos is close to 1. And then the sine is approximately the tan. But then the tangent of the angle is also the slope of the function. It's du by dx, leading back to calculus. So we can approximate the sine of the angle by the x derivative of u. Okay, and so this will then enter right here. So then the PDE becomes this. So then here we entered the derivative, and there you see we get a partial derivative in x of t times the partial derivative of u. Now we make a few more assumptions. So we assume this t is constant along the string, so it's a very good string. And then we assume the material is uniform, so rho is a constant as well. That would be this term here. So then we can take it out of the derivative. And so let's see what happens then. Okay, so then this term simplifies, rho comes out of the derivative. And T0 simplifies, comes out like this. And the alpha, beta, and Q terms are unchanged. And now I want to throw them out as well. So neglect Q. Q is small, so the gravity on the string would be very small compared to the tension, so we throw this out. And now this equation actually is known as the telegrapher's equation. And this has been used to describe electromagnetic waves in double conductors. So if you have electromagnetic waves in a conductor which has two copper wires next to each other, then this would be described by the telegrapher's equation. But I want to come back to music. Let's come back to music. So now I say that the friction forces alpha are also small, and the restoring forces beta are also small. Then these alpha and beta go. Where is this? Here. So this guy, and then I keep the wave equation. I'm almost done. 2 time derivatives equals 2 spatial derivatives. But I have the rho and T0 sitting there. And I can get rid of those also as well here on the next page, where I just divide by rho and I call c squared to be T0 divided by rho 0. And then I get what is commonly known as the wave equation. And you remember the wave equation was the ruler. It was the king of the hyperbolic kingdom, right? It's a hyperbolic PDE, and that's the ruler of the hyperbolic kingdom. So what you should have seen here is the wave equation which we study in this course is a very, very simplified version of a physical principle of an oscillating string. Okay? It will not describe the entire string because we made a lot of simplifying assumptions, restoring force 0, gravity 0, etc., etc. But it's a very good approximation of the idea of the string. So to understand the physical problem, we first need to understand the simplified wave equation. So how about the side conditions? We had a rule of thumb for side conditions. We have 2 time derivatives, so which means we need 2 initial conditions. And we have 2 spatial derivatives, so we need 2 boundary conditions. So the initial conditions, we use an initial displacement. If you look at the string, you can displace it by just pulling at it. Or you can hit it with the velocity. Like I did earlier in my little guitar play, I just hit it and then I give an initial velocity. So we have 2 initial conditions, displacement and velocity. Now for the boundary conditions, we have again the typical choices which we discussed already. For example, Dirichlet conditions. In the Dirichlet case, the string would be given some movement, or it would be given no movement, so this would be fixed ends. This is exactly what happens for the guitar, right? The string is just fixed at the end. Neumann conditions, you describe the angle, right? Du by dx, this was basically tan theta. So here you prescribe the angle of the string at the end. This is kind of a strange condition, which is maybe not so relevant in music, but it might more be relevant in the electromagnetic application. And then here the Robin condition, this was mixed, right, where you have the derivative related to the extension u. And this is a Robin condition. You can also say that the flow is kind of matching the extension there. And I give you a really cool example for the Robin condition in just a second. We can make higher dimensional wave equations by allowing, if you have in 2D x and y, then you allow the second x derivative and the second y derivative here. If you have x, y, z, then you do this as well. So all the second derivatives coming together And then these are the higher dimensional wave equations. We can also add a forcing term. This was the gravity term Q, which we removed earlier. Now I put it back in to show you that this is entirely possible to do as well. So then to summarize, we have the wave equation, we have the initial displacement, we have the initial velocity, and then we have a general boundary condition. I promised you a good example for the Robin boundary conditions, and here it is. Okay, in the trumpet the air is oscillating. You blow in the one side and then the sound comes out on the other side. So the boundary condition here is a mixture of the flow and also the oscillation of the sound wave. So this is a typical Robin kind of boundary conditions. And if you change the boundary condition, right, then it sounds like this.